Hi, my name is John Fortner, and this is my video report for Lab 2, Motion of a Falling Object. So, Lab 2 explores how an object behaves when dropped from rest, as it is influenced by the forces of gravity and drag. Um, so, the main principle of physics that this lab focuses on is Newton's second law, um, specifically the idea that the acceleration is proportional to the net force exerted on an object. So in this lab, or in contrast with the first lab where velocity was constant and therefore net force was zero, in this lab the net force is negative up until terminal velocity is reached. So in this lab, the object actually does have an acceleration, and it's based on the net force exerted on the object as a result of gravity, and then of gravity and drag in the more realistic model. So my analysis was based on a cardboard box. I picked the box because we needed an object that would fall more slowly than a rock dropped from the same height in the same environment. And the box experiences significant drag force due to its large surface area relative to its mass. And I oriented my axes so that my object would be centered at the origin and would descend straight down in the negative y direction. Okay, so here is the motion of the object in tracker. So as you can see, as the box descends, the change in position over the same interval of time becomes larger and larger as a result of acceleration due to gravity. And here's that information plotted into a data table. So this table shows the actual y position of the object in meters in each of the models. So first the model in tracker, and then in the Gauss group model that did not take drag into account, and then in the Gauss group model which took both gravity and drag force into account. And then put onto a graph, those points looked like this. So the model for drag force was not a perfect reflection of the actual motion of the object, but it was a much more accurate prediction than the model that didn't take drag force into account at all. I think that could have been because my box probably experienced more drag than a similar object might have, probably due to its very large surface area. But still, the model that included drag was significantly more accurate at predicting the motion of the object. So here's the Gauss group model that takes only gravity into account, so no drag force. As you can see, the acceleration is just a vector that has negative g in the y direction, g being 9.8 meters per second squared. And then the way velocity and position are updated is just based on, or it's based on net force divided by the mass of the object times delta t, which F net in this case is just dependent on the gravity, so it's just negative to take into account the direction times the mass of the object times g. And how that looks is this. As you can see, the position changes faster and faster as the object descends over time. Okay, and this is the model which takes drag into account. So as you can see, this one is different in that F net is actually equal to the weight force acting upon the cardboard plus the drag force acting on the cardboard. And this drag force is calculated by b times the velocity, the magnitude of the velocity of the cardboard squared, times j hat, which is the positive y direction. And so as you can see in this model, the velocity tends to flatten out toward the end. It's starting to reach a constant rate. And if you increase the time, say to 10 seconds, then you can see much more clearly that the velocity reaches this constant terminal velocity. And this occurs no matter what the initial velocity of the object is. So say the object is thrown down rather than being thrown from rest, say at negative 10 meters per second. You'll see the velocity actually decreases and comes right back to this terminal velocity of negative 4.427 meters per second. And this occurs because the magnitude of the drag force acting on the object depends on its velocity. So it will always tend toward this value such that the drag force is equal in magnitude to the force of gravity, and it'll always have this constant velocity in the long run. And that's all. Thank you.